The first talk will be by not one of the co-authors. It'll be by Adarsh Subaswamy from Johns Hopkins. And he's going to be presenting Shuchi Saria and Daniel Robinson's IGSC-AI paper that was talking about trading off cost of deployment versus accuracy for predictive models, I guess specifically geared towards healthcare applications.
Thanks for the introduction. Again, sorry Suchi couldn't be here. I'm one of her students. But I'll be talking to you about trading off cost of deployment versus accuracy for predictive models, particularly in complex domains where costs aren't elicited at the feature level. And so I'm going to be using the example of healthcare as a driving example as one of these complex domains. So consider the high-level problem of predictive models for risk monitoring. In this case, imagine that we're tracking patients in real time in the ICU, so real-time monitoring of ICU patients. And we'll talk about the problem of predicting the risk of adverse events, such as sepsis. So sepsis is a type of secondary in-hospital infection. And it's one of the leading causes of death in America. And so it's led a lot of work in building early warning systems, EWS, for forecasting the risk of septic shock. So when sepsis becomes very severe, then organs in the body begin to shut down, and this can cause blood pressure to drop to dangerously low levels. And that's known as septic shock, where it can drop to fatally low levels. And so ideally what we want to do is take physiologic data that we're tracking and use this to build models that can predict the risk of sepsis. So the information that we have available to us, one of the things is vital signs, so things like heart rate, respiratory rate, temperature. These are things that are routinely tracked across patients in the ICU. So the ICU is the intensive care unit, so you're there because you're critically ill. And patients are put in the ICU for diverse sets of reasons. Across them, though, as a standard level of care, these are general signs of your health. And so these are things that are going to be routinely monitored across those patients. Then you also have laboratory results. So these require, these have to be actually ordered by the physicians. So these generally require taking something like a blood sample and then sending that to the lab where it gets processed. You wait a while, and then those results come back, and then now you have these lab measurements which are more informative than just the vital signs. And then finally, you also have clinical history. So when patients are checked into the hospital or when they're transferred up to higher levels of care, you get their clinical history, which tells you about general things like age, race, gender, but then also the presence of chronic conditions. Do they have chronic kidney disease, chronic heart disease, things like that. And so we can really divide this information into two main categories. Routinely collected measurements, and then measurements that are available on demand. So the routinely collected measurements, as I mentioned before, are these vitals and clinical history. And so these are the baseline standard covariates that we have for all ICU patients. And so as such, they don't incur an additional cost to already being in the ICU. So these are free measurements that we have available to us when we want to build these models. But as I said, they're very, very general. You know, temperature gives you a high-level overview of if someone's suffering from an infection. And age and weight can start to tell you information about how at risk someone is given some of their other information. But these alone aren't going to give you a detailed enough picture of what's going on with the patient. So this is where those on-demand measurements come in. And here we see some example tests that physicians might order. So a complete blood count, which tells you the makeup of the blood, or a metabolic panel that can tell you whether organs are performing their job. So the kidneys remove waste products like BUN and creatinine and regulate electrolytes like potassium and calcium. And so this metabolic panel can start to tell you, okay, is this patient's kidney functioning normally? These on-demand measurements, though, come with varying types of costs. So the costs we're going to be talking about are different than the ones that were talked about in some of the morning sessions where we're talking about cost of computation. This is cost in terms of actual operational costs. So things like the financial costs of performing these laboratory tests, they require resources. So when the blood sample is taken and goes to the lab, it's put through chemical processing and it's incubated, and so those chemicals cost money. Additionally, there is wait time associated with the results. There's incubation time, and so you don't immediately get those results. And then there's measurement time associated with caregiver activities. So for these tests that require blood draws, a nurse has to get staffed, and then a blood draw can take 20 minutes. What we'll also see is that costs are somewhat complicated because there's multiple ways of getting the same measurements. So in the metabolic panel, you can order some of these individually, or they come in sort of standard packages. And so there's different ways to order them, which can change the cost associated with them. So given cost information, how do we go about learning models that are cost sensitive? And so one common approach is to adapt normal machine learning optimization with some sort of cost regularization to directly trade off model performance with the cost of the model. And so an example would be for parameter vector beta for my model. What I ultimately want to do is I want to minimize the loss on my training set, which is the loss function L, but I subject this to some sort of cost regularizer or penalty. And so this is a very common framework for setting up this cost-sensitive learning problem. The problem is that in complex domains like healthcare, and we'll go through and see an example of this, it's difficult to, the costs are actually arranged hierarchically, and so you don't have costs at the feature level because they might be arranged in, say, a cost dependency graph. And so features are going to be derived from measurements. The measurements are the results of lab tests, and then the lab tests are ultimately administered through caregiver activities. And so it's no longer trivial to assign costs to features, and so actually figuring out the form of the regularizer is the challenge here, because the costs aren't elicited at the feature level. So existing works in cost-sensitive learning can sort of broadly be categorized. Yeah, so that has to be specified. So this is manually done? Yeah. And we'll go over sort of some of the pros and cons of that. Four main types of cost-sensitive learning approaches in the related literature include classifier cascades, in which we have the choice to kind of like, a boosting framework, learn additional classifiers, which will increase computation time, but also will increase accuracy. And so there's a trade-off there. Incremental cost-sensitive classification, in which the learner needs to choose which features to collect, and then when to collect more features, when to stop collecting those features in an online fashion. Test time budgets, where at test time, let's say we pose a computational budget, which then has to be split between feature extraction and then actually evaluating the model and making predictions. So as an example, some features, like in document classification, word counts can be done through a simple lookup of a table, but perhaps computing a predefined score over an entire document will take more compute cycles. And so splitting the test time budget between then more complex features and simple features. The real problem with these three sort of classes, the cascades, the incremental cost-sensitive classification, and the structured and the test time budgets, is that they generally assume that costs are given at the feature level because they're concerned with things like compute costs, and so these are generally able to be assigned. This feature results in this much cost. But instead, we're dealing with a case where that's not the case, and so the related work is in kind of models with structured sparsity, where existing approaches, they don't tell you how to take, given that we have a cost dependency graph, given that we have some way of sort of formalizing the structure of the costs, how do we actually turn that into a regularizer? And so that's really the focus of this talk, is taking this cost dependency graph, which I'll talk about next, and turning it into a regularizer in sort of in this empirical risk minimization framework. So a cost dependency graph is just a specialized type of DAG, directed acyclic graph, where the nodes share and or relationships with parents. So again, the hierarchy going from the bottom to the top is that the features are the inputs to our models, but the features are derived from measurements. So for example, shock index is a function of blood pressure and heart rate. So it requires you to have both the blood pressure and heart rate measurements. Blood pressure is a measurement, but it can be ordered in two ways. There's the non-invasive blood pressure, which is sort of the blood pressure jacket that externally measures blood pressure. And then you additionally have arterial blood pressure, which requires, as we see, a caregiver activity. You insert a catheter into the artery and then measure the blood pressure internally. And in some cases, we take raw measurements and we turn them into features. So lactate level gets propagated down from the measurement level to the feature level. Additionally, we're not constrained to these binary and or functions. We can have multiple children. This is a simplified cost dependency graph, sort of a toy example, but you can have an arbitrary number of children, or I guess rather an arbitrary number of parents associated with these and or relationships. And so that's the relationships, but then there's the three types of costs I mentioned before, the staff time, financial costs, and wait times. So staff time is at the activity level. Again, this is really important in hospital scheduling because nurses and physicians, the hospital staff is generally overbooked. And so we want to be cognizant of how much staff time would be incurred by these measurements. And so like a blood draw takes 20 minutes of staff time. The financial costs, again, as I mentioned before, is associated with, say, the chemicals involved in performing the lab tests. And so these are elicited at the test level. And then wait times correspond to lab measurements aren't immediate, and so that's the wait time. Wait time is treated a little bit differently from staff time because ideally we can order tests in parallel, and so wait time then can be processed in parallel. So really, we're just considering the max wait time of all of the required tests for the features in our model. And so the way to deal with wait time then is you can pose an upper bound wait time, say W, and you can prune your cost dependency graph so that it only contains tests with wait time less than W.
What does it mean when you have partitions here? Meaning, it seems like there are two graphs and they don't talk to each other. So are they independent problems? Or?
It's just the structure. So in this case, it means that these blood-related measurements, so like lactate, BMP, creatinine, BUN, those require a blood draw. So they would be different patients? No, so for the same patient, I might request both a blood draw and insert an arterial line because I ultimately want shock index and creatinine level. So the bottom level shows the features. These are like the choices of features I have to input into my model. And so any subset of those features are ultimately the sort of sample space I have to choose features from. So yeah, in this case, it so happens that there's really two separate graphs, but really I'm pooling from between both of them.
There's also some sense of like, correlation among the features, right? That certain biometrics might come out to be either positively or negatively correlated, so you could use that information.
Right, and
Where is that captured?
so that would be that would presumably be at the model level. I mean, in your yeah, because there might be a trade-off then in when you're choosing features. If features are correlated, you might sort of greedily choose the cheaper features that are still informative. But that does bring up another point, which is that costs of features aren't necessarily independent in a graph like this, because the 24-hour heart rate mean and shock index, or creatinine and BUN, both come from the blood metabolic panel, the BMP test. And so their costs are actually linked together. And so I think in a lot of existing work, generally, feature costs are somewhat independent. So the goal is to turn this cost dependency graph, take this structure, this existing structure with these known costs from a known graph and turn it into some sort of regularizer. And so the way that they actually end up doing this is by drawing on connections with Boolean circuits, by realizing that the cost dependency graph is really just a Boolean circuit. So a refresher on Boolean circuits for anyone, these are just where you have variables which are these inputs to Boolean function gates. So we have like an AND gate and an OR gate here, where the variables x and y are the input, and then you have the output of the gate. So in the cost dependency graph, where multiple edges meet at a node, that's really multiple edges meeting in a gate, and then the child is the output of the gate. So a Boolean circuit is just a finite directed acyclic graph, so we're dealing with finite DAGs. Each vertex corresponds to either a basis function or one of the inputs, so either heart rate gets propagated down, or when multiple edges meet, they're going through a Boolean function. And so you can create these cost dependency graphs using and, or not functions. And so the generalization of this is I've shown you a cost dependency graph with 4 levels: the caregiver activities, the tests, the measurements, and the features. But in whatever complex domain that may be of interest, if it can be represented with an arbitrary layer Boolean circuit, then this just comes from satisfiability literature, from the SAT literature. You can take an arbitrary R-layer Boolean circuit and convert it to a 3-layer Boolean circuit that's in what's known as disjunctive normal form. And so the disjunctive normal form in this case will mean that we've got an AND relationship between the second layer and the third layer, and then an OR relationship between the first layer and the second layer. And what this is really doing is the third layer, the top layer, is where the costs are being defined. So this is, in our case, this is going to deal with test costs. The middle layer then corresponds to the different ways in which features can be ordered. And then finally, we have the features on the bottom layer. And so then this is an OR relationship. You're choosing to order a feature in a particular way. And so this links the costs to the features. And so again, you can take an arbitrary R-layer Boolean circuit and convert it to a Boolean circuit in this form. And for Boolean circuits in this form, you can then define a regularizer. So this regularizer is the relaxation. I'm not going through the derivation. It's in the paper. It's somewhat notation heavy. But this is the convex relaxation of it. You have the regularization coefficient lambda. And then you have costs that are defined at the test level. And then what this norm is doing is basically telling you where, which features, which of the corresponding features from that test you're using and how they were ordered.
So I had a question. If you are anyway going to acquire a feature, you have to conduct a certain set of tests, which means there is a dollar amount corresponding to that feature. So at the end of the day, your last function is written in terms of features.
Right.
And features cost money because you have to go through this. So how is it relevant? How does this cost of those tests upstream come into play? That's what I'm not able to.
So it's kind of it's more explicit here, but BUN can be obtained for $14, or like as a package deal where I think this would be additive, so it would be $38, or as a further package deal with an additional $30, you get all of those. So what that means is that there's 3 ways I can acquire BUN. And the point is, if I just tell you that I'm using BUN in my model, you don't know how much it costs. It really is dependent on how it was ordered, and that's what's captured in this graph. Because again, I have multiple ways of getting my features. The costs, the financial costs are associated at the test level. And so ultimately my regularizer, I wish there was a better way to explain this, but this
Why not call the test the features? The outcomes of the test. Instead, call them the features.
because that's a good question. I'm not entirely sure. I think that,
But the thing is that a test can give you a few different metrics, right? And each of them is a different feature.
No, but at the end of the, maybe we should say.
Take it with others.
I mean, that is part of it, though, that there's diversity. There's a little bit of a gap there then between the actual inputs to your model and the cost. But I think that I imagine there's something you can do at the test level to do this. And so anyway, you can take these 3-layer Boolean circuits and construct these regularizers. And so ultimately what you'll have is a regularizer for financial costs, where CK will correspond to the financial costs of those tests that are used. And then a similar term for caregiver wait times, where then those costs are the caregiver wait times. And remember, the measurement wait times are dealt with in parallel, and so for an upper bound, you prune your cost dependency graph beforehand, saying that this is the maximum wait time that I'm allowing in the model. And so we'll demonstrate kind of how this works in the application that this was applied to, which is,
You could tell me that I should contact office, but if you go back to the so you could set it up like you could relax it to a linear program, right? I'm not sure you get integral solution.
so originally, so this relaxation is going from, originally it's an L1 norm which has indicator functions, and so that's obviously not gradient friendly. So then they relaxed it to the infinity norm, but it's sort of,
What he's saying is you can find it as a mixed integer.
yeah, so they actually mentioned in the paper that you can pick an arbitrary relaxation for it. This is just one of them. So yes, I imagine that you can do.
No, but that is exact. A mixed integer linear program would be an exact, it won't be a relaxation. So it would be an exact writing of it.
Yeah, okay, so it would be equivalent because the L1 regularizer is exact. So then if it's equivalent to that, then.
Okay, anyway, let's stop here.
Right, so ultimately, the application here is predicting sepsis. So again, the motivation is that sepsis is the 11th leading cause of death in the United States. And that's pretty scary given that it's primarily an in-hospital infection with over 750,000 cases and a really high mortality rate, again, given that it's in the hospital. And so because of, there's a lot of national attention at both the federal and hospital levels to addressing sepsis. And we want to build these predictive models because what we see is that for every hour that antibiotics are delayed, the risk of mortality goes up 8%. And so obviously we can't just give everyone antibiotics because we don't want antibiotic-resistant sepsis running around. But for some fixed window before septic shock, we would like to be able to predict the risk of patients getting sepsis. So the data that we used was 7 years worth of publicly available ICU data from an academic medical center in Boston, where there were 16,000 patients, of whom 14,000 experienced septic shock. And so because this paper is about the structured regularizer, the machine learning model that's actually used is just a logistic regression, where it's trained on sliding windows of patient data to predict whether or not septic shock occurs in the next 6 hours.
For the same patient.
And for the patients in the test set, you basically break them up into like pseudo patients with the sliding windows.
So each patient is a time series?
Each patient is a time series, and so to turn them into like a cross-sectional problem, you bin them so that I take like the first 6 hours and then predict whether or not septic shock occurs in the next 6 hours. Then I take those 6 hours, predict if it occurs. Just turning it into a binary classification problem as opposed.
There was an issue with this EHRs. I mean, we played around with the EHR. The fact that a patient is inside a EHR means they might have a sepsis. There's a strong likelihood they will have a septic shock.
Mm-hmm.
Which means that it is biased towards if they did not have a septic shock
Yeah.
in the first 6 hours, you could guarantee that they will have it without even looking at data sometime. I don't know whether how you correct for this issue.
Yeah, I don't know that that's always true. I mean, sure, it's a yeah. I mean, because they're ICU patients, they're all ICU patients. It's not like there's a difference between training and test sets. But yes, there's certainly a bias in the data because they are already in the ICU. And so the full cost graph for this was created with experts, and so it has 119 nodes and 294 edges. So it's a very complicated cost graph. And so the experiment's focused on two questions. Does the structured regularizer lead to diverse models in terms of cost? And then how well does it perform compared to existing solutions? And so they compared it to a logistic regression with a cost-insensitive L1 norm as a way of inducing sparsity, and then a cost-sensitive L1 norm where necessarily the costs associated with the features were estimated in a somewhat ad hoc way because of the feature level costs, again, are dependent on how the tests were ordered. And so to answer the first question of the range of models that are available for varying values of the regularization coefficients and then maximum allowed wait times, you can learn a range of models. And so here are 4 examples. They range from model 1, which is the cheapest model, so it incurs no additional financial costs, no caregiver time, no wait time, all the way up until model 4, which is an expensive model, which incurs $168 additional financial cost per patient, 30 minutes caregiver time, and then 50 minutes of result waiting. And so,
When you say like $160, is it for every 6 hours? Like how does it work?
yes, I think those would be recurring costs because each lab measurement, every time you order a lab measurement, it incurs the cost. Yes?
So, I'm a bit concerned about these numbers because a 3% loss in AUC really means something in this domain.
Right, exactly.
Nobody would care about $168.
So this is where, obviously, healthcare is one example, but in different complex domains, it's an end user preference. So here, the difference in sensitivity between 0.61 in the cheapest model and 0.72 in the expensive model really means a lot. And so perhaps in a different application, I mean, the point is it's up to end user preferences to do this trade-off. Now, when the trade-off is involving human lives, maybe you're going to be more biased towards being willing to pay the extra cost. But the main idea is there's a range of models available. And so finally, the other experiment was comparing to an L1 norm and then an L1 scaled to be cost sensitive. And so what this shows is that AUC of the models versus the cost of the models. And so because the L1 norm has no notion of cost, the cheapest model that it recovers for a particular range of regularization coefficients is more expensive than the other 2 methods, but it also has significantly worse performance despite that cost. And then the L1 scaled performs surprisingly well given that it doesn't have the exact costs, but as we see, it doesn't really improve performance because it can't optimize those costs as the regularization coefficient is changing, whereas the group regularizer is able to sort of dynamically change with and estimate the true cost associated with the features. So in conclusion, the cost of deployment is an increasingly important thing to think about when we're putting machine learning into practice. And the main idea behind this kind of regularization-based framework is that choices of that regularization coefficient give you different models. And so it's really up to the end user to decide where they want to be on sort of this curve of performance versus cost. And so for these complex domains where there's these cost dependency graphs, this is a way of computing a group structured regularizer where once you do the work up front of creating the cost graph, the full set of models is available to you. So with that, any questions? Any questions that I can't answer, I'm happy to forward on to Suchi, by the way. So thank you.
We are running a little late. We have time for one question, one or two questions.
Are there any other applications where such cost-sensitive feature calculation, especially like the center graph?
Yeah, so it's alluded to at the end of the paper, but there's similar hierarchical costs in transportation and retail, where, as you might imagine, things aren't delivered at the individual level. They're delivered in bulk. And so, again, there's this sort of organization of products, which types of products, how many of them that get delivered. But that's just one example.
Okay. Any other questions? Thank you.